Yeah, that takes some commitment.
Yeah.
All right.
Let's be real, he probably goes better than mine.
So let's get started now today with axiomatic set theory. First, some intuition for what set theory is. Set theory is far and away the most ubiquitous field of mathematics. Almost every single field you use in math presupposes set theory. So when you go and you take your geometry class, or you go and you take your algebra class, or for those of you who were here when we did computation theory, or for those of you who were here when we did topology, we have all these separate fields of mathematics. Here's just to list out a few. What is set theory? Set theory is, in some sense, trying to identify notions common to all these different fields of mathematics and identify them all together in one axiomatic system that we call set theory. Go ahead.
Can you think of a field of math that doesn't fit into set theory?
Yeah, so there'd be something called like category theory. There's no reason that you would know what that is. But in the vast majority of cases, it builds up from set theory. And so any math class you most likely take throughout your lifetime will presuppose set theory and assume that you can use set theory in the course. So for those of you who have been doing geometry, that's why we started with some set theory in geometry. And it's perfectly valid to use set theory in geometry. Now, set theory isn't sufficient by itself to completely construct any one of these given fields. Maybe for some, but not necessarily for others. To give you an obvious taste for those of you from geometry, you know that we could have Euclidean geometry and we could have hyperbolic geometry. And so the parallel postulate can in no way be constructed from set theory. You've got to choose one or the other. To give you, for instance. So it's not enough to construct any field of mathematics. It's just that it gets to what's common in pretty much every field of mathematics. That's what set theory does. So it's the field of mathematics presupposed by every other field of mathematics, pretty much. It is intuition for what it is. And so with it being that common, it's a good axiomatic system to dive into and get into what exactly set theory is, since you've all worked with sets most likely several times in the past, even though you probably didn't even call it that. So let's start our set theory, our axiomatic system for set theory. Our first axiom here. The expression x is in y is the way we read that, is a proposition if and only if x and y are sets. All right, let's break that down for a second. First off, what does it mean to be a proposition? Make sure we remember that.
It's the same as true or false.
It's something that's either true or false, not both. It has to be true or it has to be false. That's what a proposition is. So, out of what's stated in this axiom, what terms are not defined?
The in symbol and sets.
The in symbol here and set here. And so in set theory, our only two primitives are the in symbol and set. That's it. Those are our only primitives. Every other definition will ultimately be in terms of set or that in symbol. Now that in symbol, what is it?
It's an wait. It's a predicate.
It's a predicate. More specifically, it's a relation. What's a predicate?
It is something that returns true or false.
Yeah, it takes terms and it spits out true or false. A relation is a two-term predicate. It takes two terms and it spits out true or false. So, every time we evaluate this, it's either going to be true or false. It's going to be a proposition. So the expression x is in y is a proposition if and only if x and y are both sets. So for all sets x and y, understand now that our quantifiers will always be talking about sets. Every time we see for all x, it's for every set. That's how we're going to read that. So for every set x and every set y, we have x is in y, or it is not the case that x is in y. This is the only time I will use the exclusive or, if you remember that.
Yeah,
Inclusive
okay.
or is like this.
It looked like an arrow to me for a minute.
Yeah, that's what exclusive or looks like, is or like that. Let's remember the difference between inclusive or and exclusive or. Inclusive OR means at least one of them is true. Maybe they're both true, but at least one of them is true. Exclusive OR means one and only one is true. When you go to a restaurant and your menu says that comes with soup or salad, they mean it in the exclusive OR sense. You can get the soup and not the salad, or you can get the salad and not the soup. You can't get both. If I say you have to take calculus or physics to take this class, now I mean it in the inclusive sense. It's okay if you take both, but you have to at least take one. So that's the exclusive OR, meaning at least means one and only one of those has to be the case. So either X is in Y, or it is not the case that X is in Y. Okay, now, this axiom, at first glance, might seem kind of like a silly axiom.
Yeah.
I'm saying X is in Y is a proposition if and only if those are sets. Isn't it always X in Y? Isn't this always a proposition?
Why would it be?
Why wouldn't it be? That's a relation. And so it takes two things and spits out true or false. What on earth is this axiom even giving us? What a waste of breath.
Oh,
Alright, so historically, it took a while to come up with this axiom. Set theory was developed over time.
Yeah.
It's not like someone sat down one day and just developed all of set theory. There was an approach at it which failed, and another approach at it which failed, and another approach at it. It's like, okay, we're getting somewhere. So it took time to develop this as an axiom. Historically, what happened? So Bertrand Russell, he's a pretty famous logician.
Yeah.
Him and a guy by the name of Alfred Whitehead, they wrote this series of books called Principia Mathematica, but they basically made an attempt at developing everything in mathematics from logic, including set theory. And the set theory they developed is what we now refer to as naive set theory. Their set theory, unfortunately, doesn't work for them. Bertrand Russell, he has it recorded, I think, in his History of Western Philosophy, one of the books he wrote. Talks about how he would wake up from dreams, wake up from nightmares, where people were throwing his books out and burning them. Because it just doesn't work, unfortunately, for him. But the work they did was good in developing set theory, and here's the problem that they ran into. Because for Bertrand Russell, initially he would have viewed that as kind of a waste of breath, so to speak. So what happened? We came across something called Russell's paradox. Here's what it is. Let U be the set of all sets that don't contain themselves. That's a lot to swallow. Let's define it explicitly. For all X, X is in the set U, if and only if it is not the case that X contains itself. So pick a set. Does X contain itself as a member? If yes, then it's not in U. If it doesn't contain itself as a member, then we throw it in U. And so we're gathering up all those sets.
Okay, could you give us like an example of this? Because it's hard for me to visualize.
I cannot write this thing out.
Okay.
Well, she's asking just for just for an example of a set that would be in there. What is a set that would be in U?
Yeah.
Or not be in U?
Like what?
A set that doesn't contain itself?
Yeah.
So here's a set that doesn't contain itself.
What is a set that does contain itself?
If I say X is equal to the set containing X.
Okay.
Here's a set that contains itself as an element. 1 does not contain itself as an element because 1 is not equal to the set containing 1. Those are two different things, and we'll find out exactly what 1 is in terms of its set theoretical definition.
Okay.
So, since this set does not contain itself, here's one of the things in U.
Yeah.
Gather up all the things, all the sets that do not contain themselves, and throw them together in a collection called U. That is what U is. It's a set of all sets that do not contain themselves. And this is the type of set that naive set theory, imprecise set theory, enabled us to construct. Let's see what the problem is. Question. Does U contain itself? U is a set of all sets that don't contain themselves.
So if U
So does U contain itself?
well,
Well, let's think. If U contains itself, what does that mean?
that is not in U.
U is a set of all sets that don't contain themselves.
Then U does
If U
not.
contains itself, then U is not in U.
Yeah.
So if U contains itself, then U doesn't contain itself.
But if it doesn't contain itself.
Because U is a set of all sets that don't contain themselves. So if U's in there, then U can't contain itself. So U's not in there.
But if U's not in there, then
So, you being in there is impossible, because at least it not being in there contradiction. So now what happens if we say u's not in there? What does that mean? If u is not in the set of all sets that don't contain themselves, then that means u must be one of the sets that contains itself.
Yeah.
So it just goes back and forth.
So if this is false, then it's true. But if it's true, then it's false.
So
what is it?
it's not a set. Well, we shouldn't define it as a set.
So u and u, is this true or false?
It's a kind of a bad question.
It's a bad question. Because if it's true, it's false, and if it's false, it's true. So this thing right here is not a proposition.
Mm-hmm.
It's not something that's either true or false. So let's go back and read our axiom again. The expression x is in y is a proposition if and only if x and y are sets.
Okay, that makes sense.
Conclusion is u here is not a set. Gathering up all the sets that don't contain themselves and throwing them in a collection, whatever that collection is, it's not a set. Don't ask me what it is, I'll tell you what's not. And what's not is a set for sure.
Yeah.
Okay, yeah, that makes sense.
And so we have to be careful about just trying to define sets into existence that aren't sets. Right? Saying, consider the set of all sets that don't contain themselves is kind of like saying, let's consider the prime number 4. What can you tell me about the prime number 4?
It's not a prime.
It's not a prime number. Me calling 4 a prime number doesn't magically make it so. And so just because we call this collection of things a set, doesn't magically make it a set. So it is in fact not a set.
Is that true for any self-referential set? Like they're not set? Like, can you have any set that would reference itself? Or is that impossible?
Can we ever get self-reference in a set? We might be able to, but we won't be able to get it in a straightforward x is equal to the set containing x kind of way. But that does not follow from this axiom. Okay. So, Russell's paradox, so that gives you some sense of why that axiom needed to be introduced, and how early on thinking about sets, we were a bit fast and loose, enabling us to get into bad states, concluding contradictions. Okay, so now we got our first axiom, and we've got our first two primitives. This is a member of symbol and sets. So now we're going to come up with a bunch of definitions. Our first definition, x is not a member of y. What does that mean? X is not a member of y. That is logically equivalent to, it is not the case that x is in y. Oops, I think I already accidentally used a symbol before I defined it. Next, x is a subset of y. What does that mean? It means for all a, if a is in x, then a is in y. Everything that's in x is also in y. That's what it means for x to be a subset of y. As a concrete case, if I look at 1, 2, 3, this is a subset of the set 1, 2, 3, 4. Everything that's in here shows up in here. That's what it means to be a subset. So x is a subset of y if and only if, for all a being in x implies a is also in y. Let me point out something strange here that you are most likely not comfortable with. What are the only things that we can stick inside of sets?
The only things we can stick inside of sets?
Yeah.
Variables.
We can stick anything inside sets, but what do you mean?
The only things we're going to ultimately be sticking in sets are other sets. That's another thing that you need to pay attention about from here. X is in y is a proposition if and only if both x and y are sets. What goes inside of sets? Just sets. And this is going to be very strange. And you are not going to be comfortable thinking about it this way. There's a joke that sometimes helps get the point across. I think the physicist in the joke is supposed to be Richard Feynman. Someone. Richard Feynman, he's given a lecture. And in the lecture, he's explaining how the Earth is in the universe and that the Earth is just actually sitting out there in space, completely unsupported. And he explains in his lecture that you don't need something supporting the Earth, it's just there. Some old lady hears the lecture. After the lecture, she comes up to Richard Feynman and she's getting after him, telling him that it's a terrible lecture. The Earth is not just sitting there unsupported. Everyone knows that the Earth sits on the back of a turtle. Richard Feynman says to the old lady, okay then, what's the turtle standing on? The old lady, she smiles. She says, very clever, young man, but we all know it's turtle all the way down. Turtle all the way down. In set theory, when we construct these things, it's going to be sets all the way down.
Wait.
Jumping all the way ahead, let me just show you what the number 4 looks like in set theory. That's what it looks like.
So it's just.
Set to side, a set to side, a set to side, a set to side, a set.
So the only set that actually has something in it is the empty set?
The empty set has nothing in it.
Well, yeah. That's like the only,
The only set that has nothing in it is the empty set. Everything else has something in it.
but it's just other sets.
That is correct. The only thing we can stick aside sets. Now, when I do my examples, I'm going to do feel-good examples. My examples all stick whatever we want in there to help us feel good and get intuition about sets. But when it comes to the theory that we're developing, when we're actually proving things, we're talking about the axioms, remember, it's just sets.
Why?
That's what we do in set theory. We construct everything from sets, and everything has its set theoretical definition. It's all sets.
So then how do you like dummy, like we went over set builder notation today in geometry. How does that work if it's just sets?
We'll get set builder notation. So we'll get all that. But yes, it's all just sets. So this should not feel good to you. It should bother you. You should not like it.
Yeah.
If you don't like it, good, you're thinking about it. If you like it, start thinking. You shouldn't like it. It should bug you. Okay. So continuing with our definitions. X is not and Y means it is not, we already did that one. Starting with this one. X equals Y. Now, equals is a concept from logic. It is the law of identity in logic that gives equality its meaning. So what on earth am I doing trying to define equality here? So this is called extending the definition. We are going to extend the definition of what it means for two sets to be equal. Intuitively, from logic, I already know that the set 1, 2 is equal to the set 1, 2. That is true just from logic, forget whatever sets are, because we have identical symbols on both sides of equals in identical orders.
Yeah.
So everything is identical with itself. That's from logic. What this extension of identity is ultimately going to give me is that 1, 2 is equal to the set 2, 1. We want this set and this set to actually be the exact same thing. And so, intuitively, that's what this is going to give us. What it means for two sets to be equal to each other. It means that everything in the first set is in the second set, and everything that's in the second set is in the first set. This set is a subset of this set, and this set is a subset of this set. Notice that with this definition, these two sets are still equal. Pick any element you want out of here, it's in here. Pick any element you want out of here, it's in here. So everything that's in here is in here, so this is a subset of that. Everything that's in here is in here, so this is a subset of that.
Yeah.
Okay. So there's set equality and then proper subset. X is a proper subset of Y. Sorry, X is a proper subset of Y means that X is a subset of Y, but X is not equal to Y. And this means that everything in X is in Y, but there has to be at least one thing in Y that does not show up in X in order for X to be a proper subset of Y. So the set 1, 2 is a proper subset of the set 1, 2, 3. There's something in this set that doesn't show up in this set. So this is a proper subset of this. On the other hand, 1, 2, 3, this set is not a proper subset of that set. It is a subset though.
You just call it a proper subset.
Proper subset. Proper subset functions a lot like less than. Subset functions a lot like less than or equals. Right? When I say X is a subset of Y, that means X is somehow less than or the same as Y. When I say X is a proper subset of Y, that in some sense means X is actually smaller than Y. There's actually something in Y that for sure isn't in X.
Yeah.
Common intuition to accompany those definitions. Okay. So with that, some basic definitions. Let's get now to our second axiom. Our second our existence axiom. So there exists a set that contains no elements. Or in other words, there exists the empty set. What does this mean explicitly? It means there exists some x, some set, such that for every other set y, y is not in x. This is very similar to in our other systems when we had like there exists there exists an additive identity element.
Yeah.
This is going to function a lot like an identity element in set theory. You can think about it as our union identity element.
Gotcha. Okay.
Okay. So our axiom is that there exists some set that's empty.
Wait,
Now,
doesn't that come straight from axiom 2? Oh, sorry.
no. Now we're going to prove that there exists a unique set, such that for all y, y is not an x. This says there's at least one empty set. We're going to prove that there's in fact one and only one empty set. So I'm guaranteed that there's at least one empty set from the axiom. Our first proof here is going to be to prove that, and there's only one empty set. So we got to prove that the empty set is unique before we can define it. So then that symbol we will define to be the empty set. Remember to last week, in order to define a term, that would be defining a term. In order to define the term, you must first prove it's unique. So we'll do our uniqueness proof, and then that symbol will be well defined. And that symbol will signify the empty set. But first, let's prove it's unique. So how should we do this proof? Pretty standard formula for uniqueness proofs.
You get by way of contradiction.
Yeah, let's assume by way of contradiction that there are two empty sets that aren't the same thing, and prove that they actually are the same thing.
Mm-hmm.
Contradiction. So there couldn't have been two sets out there that were the empty set. So assume by way of contradiction that there exists A and B such that for all y, y is not in A. For all y, y is not in B. And A is something different from B. It's not equal to B. So assume that there exist two sets out there such that the first set, A, is empty. For all y, y is not in A.
Yep.
Anything you find, it's not in A. A is empty. Similarly for B. For all y, y is not in B. So A and B are empty. We're going to assume that they are different from each other. And our contradiction is going to be proving that they are in fact the same as each other. So I'm now going to prove that A equals B, contradiction. How should I prove that A is equal to B? What does it mean for set A to equal set B?
Right, there's subsets of
Right here. X equals Y, if and only if X is a subset of Y and Y is a subset of X.
Wait,
So I'm going to prove that A is a subset of B and B is a subset of A.
Wait, if they both contain nothing, they're both subsets of each other.
Right. So how do I prove that A is a subset of B? So to observe that for all y, y in A implies y is in B.
But y can't be an A.
So let's think about this for a second. This is what it would mean to say that A is a subset of B. It would mean to show that for all stuff in there, if it's in the first set, then it's in the second set.
Right.
So for all y, if it's in the first set, then it's in the second set, is our definition of A is a subset of B.
Why does that implication hold?
Why does that implication hold? What do we know about y in A?
It's not possible.
It's not possible. So evaluate this expression, y in A.
It's false.
It's false.
False implies anything.
False implies anything is
True.
true, vacuously true.
Oh, yeah, I forgot.
So this is always true. Right?
Yeah.
So that And so I am given that A is a subset of B. Similarly, since for all y in B implies y is in A, y in A, no one saw that, not recorded. Then what?
They're subsets.
Then B is a subset of A. That's what it means for B to be a subset of A. It means for all y, if it's in B, then it's in A. 4. Therefore,
Are they equal?
yeah, if A is a subset of B and B is a subset of A equals B. Contradiction.
So there's only one empty set.
Right, so the empty set is unique. And we're not going to write out a separate definition saying that that symbol means it. We're just showing a definition in the theorem with it.
Oh, I feel so wrong. I really don't like that.
What don't you like?
That we're using vacuous to tree together.
Well, intuitively, that makes sense though. How do I know that these two sets are the same thing? Everything in here is in there, and everything in there is in here.
I mean, they both have nothing in them.
So, the logic you would use to explain to a child that two empty sets are in fact the same set is going to use that vacuously true stuff, and they'd be comfortable with it. Okay, so that is our first theorem, and now the empty set, that symbol is now defined. It is the one and only empty set. Okay, so we now have a defined term. We've defined a bunch of different relations on sets. Now we have a defined term in our system. Haven't defined any operations yet.
Okay.
Okay, so our next axiom now, axiom 3. If x and y are sets, then there exists some other set M, there exists M, such that M is a set whose only elements are x and y. If x and y are sets, then there exists some set M whose only elements are the sets x and the sets y. We denote M as being equal to curly brackets x, comma, y, and curly brace. So we are now defining this notation for the first time. So now curly braces being used to talk about sets, ultimately that's going to come from this axiom.
Why is that an axiom? Does that really have to be an axiom?
Well, so far, what sets do we know exist in our system?
The empty set?
Here's what our system consists of so far.
Okay.
So we definitely need some axiom to start getting more types of sets. And so now we know at the very least, hey, we can take the empty set, and we can stick them together in a set. And now that's well defined. And that's a set that we can have in our system.
Well, isn't that just... Wait.
No, that's very different from just the empty set.
I'm sorry, what's happening?
Axiom 3. If x and y are sets, then there exists M, where M is a set whose only elements are x and y. And we denote M by curly brace x, comma, y, and curly brace.
Okay.
That makes sense, I guess.
So this is the axiom that gives us all that curly brace notation that we like to use to talk about sets.
Okay.
It comes from this axiom ultimately. Okay. Writing it out more explicitly using our logical notation. For all x and y, for any two sets you choose, there exists M such that A is in M if and only if A is x or A is y.
Okay.
In other words, M is a set only containing x and y. Good so far?
Yep.
Okay. Now, let's prove that the order that we list elements out in a set doesn't matter.
Sweet.
I told you intuitively we want that with our sets, but now let's prove that that is in fact the case. That the set containing xy is equal to the set containing yx.
Okay.
Alright, so let's write this out. How do we prove that two sets are equal to each other?
They're subsets of each other?
We need to prove that they're subsets of each other. The way I prove they're subsets of each other is I need to show everything that's in here is in here, and everything that's in here is in here. Right? Okay. So let's start out with, say that A is in XY. I need to show that that implies it's also in here.
Okay.
So if A is in XY, what do I know?
A is X or A, or yeah, A is X or A is Y.
Yeah, what does it mean to be in the set XY? It means A is X or A is Y. That's exactly what it means.
Yeah.
So that gives me that A is equal to X or A is equal to Y. Now going back to logic, or is what do I want? Look, I'm trying to show that A is in here.
Yeah.
How do I know A is in here? I know A is in here if A is equal to Y or A is equal to X.
Yeah.
Yeah.
I have A is equal to X or A is equal to Y. The or is
The or is flip?
What?
No.
this gives me that A is equal to Y or A is equal to X. How can I say that?
Oh, are you saying it's
Oh, because you can replace the.
it's reflexive?
Addition is another one. 3 plus 2 is equal to 2 plus 3. What's that property on addition?
Commutative?
Commutative. So or is commutative.
Did we cover that in logic earlier?
We said it. I don't know if I bothered writing out the truth table for it. How would you prove that? You would show that alpha or beta has the exact same truth value in a truth table as beta or alpha.
Wait, isn't that true for all logical operators?
No, it's true for or, it's true for and. It is not true for implies. Alpha implies beta is drastically different from beta implies alpha. It is true for logical equivalence, and then it doesn't make sense with negation.
Right. Okay.
Okay, so now I know A is equal to Y or A is equal to X.
Oh, well, sweet, you're done.
So then what does that tell me? That's exactly what it means for A to be in the set
YX.
YX. So if A is in XY, that gives me A is equal to X or A is equal to Y. But that's the same thing as A equals Y or A equals X, which gives me that A is in X or Y.
Yep.
Or is in
YX.
the set containing Y and X. You follow that?
That makes sense.
Just using the definitions here. What is the definition of A is in the set M, where M is that thing? Means A is X or A is Y. So if it's in there, A is X or A is Y. Pretty straightforward. Now we could just go the reverse direction. If A is in here, that implies A is equal to Y or X, but that's logically equivalent to this, is logically equivalent to this.
Yep.
So if this is the case, and this is the case, and if this is the case, and this is the case. So that gives me that A is a subset of B, and B is a subset of A. Therefore, A is equal. Oh, we didn't name those.
We did not.
That was probably confusing. So that gives us that this, the set XY, is a subset of the set YX. That's looking at it this way. And the set YX is a subset of the set XY. 3, therefore, there we go.
Are we going to prove that duplicates don't matter?
Kind of.
Okay.
Okay, so that ends that. On to our next definition. By definition, we define the singleton element set as a set containing two elements. So notice, so far, we only have this notation defined when I stick two sets in there.
Oh, yeah.
Right now, as it stands, this, the second containing one, is not defined.
Yeah.
So now I'm going to define what I mean by the second containing one.
Okay.
And it means the second containing one. And now you see, now duplicates don't matter. Intuitively, anytime I have 2, I can replace it with 1. It's the same thing.
Gotcha, okay.
So that's why duplicates end up not mattering, is going to be ultimately from that definition.
So, does that allow us to write sets with any number of elements in them now?
Well, this enables us to write sets with any number of elements in it now. Any finite number you choose, I can now construct a set that has that many elements.
How do we know that?
How do we know that? So first off, I'm given the empty set. That was given to us right here.
Yes.
Now this one tells me that for any 2 sets, I can stick them together.
So we can have.
So now I can have the set containing the empty set and the empty set.
Yep.
So I can have that one. And if I wanted, from this now, I could also have this notation defined. The set containing the empty set. That's now defined.
Yep.
Okay. Now this one, once again, says for any 2 sets, I can collect them together in another set.
Okay.
So I can take this set together and collect it with this set. And I can now talk about this set.
So that allows you to write any finite number of.
Well, so far, all our sets, strictly speaking, are just going to be pairs of 2 things in it every time. But when I say arbitrarily large, I mean using an arbitrary number of symbols.
Can we have infinite sets? Yeah.
Yes, because of the way that we're going to define what a 3-element set is. So you'll see it. I'll give you a taste. You'll get a taste of it right here with this. Really quick, let's talk about ordered pairs.
Okay.
So if you've done some math classes before, the 2 types of things that are always coming up are sets and ordered pairs, or ordered lists.
Mm-hmm.
Sets of things and ordered list of things. So you probably come across before that. What's a function? If we were in like an algebra class, a function is just a set of ordered pairs. With some rule, every input has a unique output, but it's ultimately just a set of ordered pairs. So sets and ordered pairs are very commonly the things that we use to construct things. So let's get ordered pairs out of the way.
Is that the actual definition of a function?
That is the set theoretical definition of a function. There's the notion of a function that you have all the way in logic. And then, and then you get a more restricted notion of a function. And so we can talk about a function, and we'll even talk about a function here in a second, a functional relation. So here's functions in terms of logic. Here's functional relations. Here's what's going to be set theoretical functions, the things that you talk about as functions in your algebra class. We just keep restricting the notion. And we say, from here on out, every time we talk about a function, we mean one of these things, not necessarily one of those things.
Can you remind me what a function in logic is?
No.
Okay.
Because it's just a notion that we use.
Okay.
Right? One of the ways we think about a proposition is one of the ways we think about a predicate is a proposition valued function.
Yeah.
And so it's in some sense part of the meta theory and not strictly part of the theory.
Okay.
And so you have to develop the theory, and then once you develop the theory, you can nail down, from here on out, here's exactly what I mean by that word. But first you have to build a theory to nail it down. And we'll nail down a notion of a function here in set theory. Anyways, so we were right here with that notation. Let's really quick define an ordered pair now.
Okay.
What is the ordered pair xy? That is defined to be the set containing x together with xy.
Why would it not be the set?
Let's give a concrete example really quick. 1, 2, then is going to be equal to the set containing 1 together with the set containing 1, 2. That's what it is defined to be.
Why did we choose that definition?
Notice that this is always enough information for you to reconstruct which one came first. Notice that 1, 2, one of the things we want about ordered pairs, a property of ordered pairs we want is we want xy to equal ab if and only if
X
x equals a and y is equal to b. That's the only time we want ordered pairs to be equal to each other. So the ordered pair 1, 2 is very different from the ordered pair 2, 1. In terms of your real number plane, we use ordered pairs to plot points, and when you talked about the point 1, 2, you meant 1, 2. And when you talked about the point 2, 1, you meant go over 2 and up 1. So here's a point 1, 2. Here's a point 2, 1, and those were very different things.
Wait, so 2, 1 here would be the second containing 2 and the second containing.
So 2, 1 here would be exactly 2, comma 1, 2. And those are very different things. And how can you figure out which one comes first? I give you this thing and I give you this thing. You just need to check, is this one a member of that or is this one a member of that? Whichever way the member relation goes tells you which one comes first.
How so?
Because up here, I know that the 1 comes first because 1 is in 1, 2. Over here, down here, I know the 2 comes first because 2 is in 1, 2.
Oh, I see what you mean.
And so you can always say, which one was my left-hand element? Was it this thing or this thing? Because the order I wrote here is kind of arbitrary. Let me rewrite the exact same set. This is still the encoding of that. How do I know what came first? How do I know which one belongs on the left-hand side here? It's the one that's a member of the other. This is not a member of that. This is a member of that.
But then how do we...
And so whichever one is a member of the other goes on the left-hand side, and whichever one wasn't the member of the other goes on the right-hand side.
How do we know that set isn't talking about the ordered pair 2, 2?
This one?
Oh, I guess that makes sense. Wait.
2, 2, you still get the same thing. So let's think through 2, 2.
Yeah,
Because it is a little bit weird.
that is strange.
2, 2, we'll keep that. 2, 2 is the same thing as 2, 2, comma 2. But notice, the second thing 2, 2 is not in there. 2 isn't there. You could have not written one of those 2's and had it written out that way. Still the same thing.
It's still the same thing.
But it's still, notice, that is in there and that is not in there.
Wait, okay, so why do we bother writing out 1 and the second containing 1, 2? Why don't we just write 1 and the second containing 2 for the order pair 1, 2?
2 isn't in the second one.
Oh.
Yeah, how would you know which one is a member of which one?
Well,
And so this relation is always giving us our order to things. You're going to come, when we get to it, you're going to find out that this means the exact same thing as a less than in arithmetic. And so this is our thing, always ordering things for us.
that's very strange.
And so whichever one makes the relation true, it tells you which way you order it.
Huh. Okay.
So that's what we mean by an ordered pair. Now, what do we mean by an ordered triple, x, y, and z? That is just shorthand for the ordered pair where the left-hand side is also an ordered pair.
And that,
So this 3-element set is the ordered pair containing x, y together with z.
and that can be abstracted to any...
And this works for any n number.
Okay.
A1, comma, A2, comma, dot, 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 comma, an is equal to the order pair where the first one contains A1, A2, dot, 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 A sub n minus 1, comma, out of print, see there, A sub n.
Yep. Okay.
And yeah, it generalizes to any number that you want. So always keep in mind that anytime you're looking at a list of things, it doesn't matter if it's a list of 100 things, it's really just an ordered pair. Where the left-hand side is a 99 element list, and the right-hand side is just one element.
And you can just take that all the way down.
And it goes all the way down to just an ordered pair.
Okay.
Always having its set theoretical counterpart. So it can always be defined in terms of sets, and we can use sets to get order. So one of the thoughts you may have had, like our intuition for sets is two things, is It's an ordered, unique collection. Lists, on the other hand, sets are unordered, unique collections. Lists, on the other hand, order matters and duplicates matter. And yet we can capture that functionality just using sets.
Can you write out an ordered triplet in set notation real quick? What does that look like?
Do we dare try it?
I think we shall.
Hopefully it doesn't blow up on us.
It shouldn't. Not much. Hopefully.
Alright, so let's try writing out the ordered triple 1, 2, 1. You're saying something like that, right?
Yes.
Okay, so first off, let's just think it through one step at a time. This is the same thing as the ordered pair, containing the ordered pair 1, 2, together with 1.
Yep.
Like that. Now what exactly does this mean? Looking at its definition, an ordered pair, it's the set containing the left-hand thing,
Which is 1.
1, 2.
Oh, I see. Okay.
It's the set containing the left-hand thing together with the set containing the left-hand thing
And the right thing.
and the right-hand thing. Right?
Mm-hmm.
Now I gotta plug in the definition of those in terms of set theory.
Yep.
So this is equal to writing out this piece. And now, oh, I'm missing a bracket there, right?
Yeah.
Okay, now write this bracket. Sorry. Now, this thing again, that is a set containing 1 together with the set containing 1, 2, and that, still inside this one, comma, 1, then this bracket, then our last bracket.
Wait.
I think we did it all, right?
Did,
That closes you, that closes you, that closes you, that closes you. Here's the order pair 1, 2. Here's 1. Here's the order pair 1, 2 again.
Okay.
And there it is.
There's no feels like there should be a duplicate in there.
There's not going to be. Why isn't there going to be? There's the order pair 1, 2 by itself, and then the other 1, 2 isn't in the same set. It's in a different set.
Okay.
So notice that your set here, your outer set, only has 2 elements. This thing and that thing, which are for sure different. And then look inside this one, that has 2 elements, which are for sure different. That has 2 elements. And you can look, it's going to be 2 element sets aside, 2 element sets aside, 2 element sets, building these things up.
That makes sense.
And each time, they're different from each other. Okay. So, I think we're ready for axiom 4, right?
Yes.
Okay, axiom 4. If X is a set, then there exists M as a set such that the elements of M are the elements of X. We denote it as M is equal to the union on X. This is strange because this is not the way that we're used to doing union. And this axiom is going to give us our first operation, so we're going to start being able to define set operations from this thing.
Wait.
So let me erase that. I've got an example. We'll do this example to help this out. Make sense of it?
Wait. Do you want to go over the precise definition first?
Yes. All right. So using precise notation, what does that mean? It means for all x there exists. Well, no. Let me do this first, and then we'll make it make sense. What is M going to be? So M here is going to be equal to the union on X, which is going to be equal to, in this concrete case, M is going to contain the elements of X. What are the elements of X? The set containing AB and the set containing CD. What are the elements of X? AB and CD. So M is going to be the set AB, C, D.
Oh, I see.
Now we'll go over the precise definition. For all X, here's an example of X. There exists some M out there, such that for all y is going to be iterating over each of these things. Y is in M, if and only if there exists some set U would be referencing like this set right here. There exists some U in X where Y is in U. So a Y would be like this A thing. So Y would be like this, U would be like this set. And let's say it one more time. For all X is this entire set, there exists some N, such that for all Y, so Y starts out being A, B, C, D, each of these. For all Y in M, for all Y, if Y is in M, if it shows up in here, that's the case if and only if we can find a set U in X such that Y is in U.
How does that allow us to union two sets? Like, we're talking about union of X, not like X and union Y. Does that make sense?
So unioning X enabled us to union together in the sense that you mean it, two internal sets.
Okay.
So if I have some set here, X equal to AB, Y equal to CD, right?
Mm-hmm.
And I want to union those together. How do I do it? Well, from this axiom over here, I know that there must exist some set now containing X and Y. And now, from this axiom, I can union it, and the result is a set containing the elements of these things right here, which will give me this exact case.
Okay.
So you're just not used to sticking the sets inside of another set before you union them.
Yeah, but that makes sense.
And we'll define that notation. We will say, what exactly does it mean to take set A union with B, using notation that you've probably seen before. We're going to define this to mean that is the union on the set containing A and B. And that's going to be its exact definition.
Okay.
So that gives you the union that you know and love. But it comes from this axiom.
Okay. Yes.
And so now I'll just read the high level one again. If X is a set, so remember, X is going to be a set containing some sets we want to union together. If X is a set, then there exists M as a set such that the elements of M are the elements of the element of X. We denote M as being equal to the union on X. And so keeping track of our primitives now, there's an operation that's undefined.
Well, okay, yeah. Okay.
And then we'll use union now to define all the other operations we want on sets. They'll all be defined in terms of union.
Okay.
Okay.
Wait, why couldn't we define, why does union have to be part of an axiom, and why can't we define it as an implication?
Well, notice how we were stuck before. So far, we were stuck with 2 element sets inside 2 element sets inside 2 element sets. I could never get a 3 element set or a 4 element set. With union, now I can. This is now the type of set we can talk about. We haven't defined this notation yet. This is just an example. We'll define this notation. But the point is, give me 2 sets, I can now union them together. That's essentially what it gives us.
Right. Okay.
Yeah. Because up till now, all we knew is that if you had 2 sets, I can take any 2 elements out of those sets and put them together in a set. Or I could take the 2 sets themselves and put them together in a set. But I didn't know that I could just take the elements of a set and stick them together. Okay, so the next definition here is going to be now defining this actual notation that we've already been using. So let A, B, and C be sets. We define A, B, and C. It's almost identical to what we did up here. We define it to be the union of the set AB
And the set C.
and the set C union together. So it's almost identical to how we defined it up here. A little bit different.
That is understandable. That makes sense.
So now we can get a 3 element set, which is something that we could not get before.
Okay. And that allows us to get any finite number of sets? Finite number of elements in a set?
Yeah, and then we have this recursive definition. Let A1, A2, AN be set. We define the n element set to be the union on those for all n greater than or equal to 3.
What's that part for?
This notation doesn't make sense if you try and pick n to be 0.
Oh,
It doesn't. Here's the simplest case where this notation now makes sense.
what about 2? Why wouldn't that work? For n equals 2.
I guess 2 could have worked. So we could have stuck a 2 there if we wanted.
Oh,
But we already have the 2 defined.
Ah,
So this was just to give you a sense for it. Here's really what the definition would have been.
fair enough. Okay.
Make sense? Now,
Wait, we don't know what 3 is.
wonderful.
How do we even talk about that?
So, important note here. These 1s, 2s, n's, whatever, these are not yet the natural numbers. This is a subtle point. And will probably do more to confuse than to help. But these are, sometimes they're called meta numbers. But these are not the natural numbers that we know how to do arithmetic on. They are just unique symbols.
Weird.
And that's all that they really mean is some unique symbols. You can think about them as just putting tick marks. 1 is this, 2 is this, 3 is this, 4 is this, and we could just be ticking away just to give a unique identifier to each one.
So they're like a
But the point is that this only makes sense under finite conditions. You can't go infinite because you couldn't do this an infinite number of times. So they're just unique identifiers.
sounds like logically equivalent to having a different letter.
Yes.
Okay.
And then this would be for all the letters, it would be letters in some order, and this being all the letters after the first 3 letters. We can't get away from the language.
Wait, so
So we have to use the concept of 3 before we have a definition of 3.
does that mean that that's an undefined term? Technically?
It's not an undefined term in that sense, because when we're developing our logical systems, introducing terms, variables, is never adding to your theory. Just because I use a notation x sub 1 and x sub 2, those aren't undefined terms in our system. They're symbols of logic, and we're okay.
Okay. But there's really no way to do that without saying n greater than or equal to 3.
Well, that's just giving you intuition for what we're talking about.
But there's no way to make the definition where it doesn't include that part. Like, can we get around that having to use the idea of 3?
Get around somehow using the idea of 3? No.
Really?
That would be like trying to do this without the idea of 2. We have ideas for what we mean by these things.
Yeah.
And you can't get around that. So a theory doesn't introduce the concept to your brain. The theory nails down exactly what we're going to mean by that concept from this point onwards.
But we're not talking about exactly what it means because we don't know what 3 is.
That's correct. And to come up with an exact definition for 3, we're going to restrict our notion of what we mean by 3. And once we have a 3 defined, here's what we mean from 3 on out in our theory. So you have to use the concepts before you nail down exactly what they mean. And there's no way around that.
Annoying. Okay.
You run into the similar, it goes back to, I don't know if you remember Aristotle's theory of knowledge. Talk about how we have to know the concepts before we can ever build the abstraction for it.
Okay.
It's a similar type of thinking here.
Yeah,
We can't construct the abstraction without the concept first.
that's understandable.
Okay, but yes, good complaint.
Okay.
Very normal complaint. Okay, we good with this?
Yeah.
Pressing on. Here we go. Okay. Can I get all 3 columns? Yes. In case I need to reference anything there. Okay. A couple definitions. These definitions we're saying up just to get to axiom 5. Wording, axiom 5 is the tough one. And it's the one that gives us all the cool stuff.
Okay.
Okay, so our next definition, a relation R is said to be functional In other words, it acts like a function, the way that you know and love functions. What's the property of functions? Tell it to me like I'm in 6th grade.
There's a unique left-hand element for every right-hand element.
Okay, they're not good.
Other way.
Other way around.
For every input, there's one and only one output. Every input has a unique output.
Oh yeah, I got that.
I can't take one input and get 2 different outputs, otherwise it's not a function.
So for every right-hand element, there's a unique left-hand element, right? In your order term.
You're going
Yeah.
back into the 6th grade.
So for a function,
Basically the same.
if x is equal to y, that implies f of x is equal to f of y. If the inputs are the same, the outputs have to be the same.
Yeah, right.
I can't have one input going to more than one output. A function's one-to-one if you have the inverse. If f of x equals f of y, implies x is equal to y, then the function is what we call one-to-one.
That makes sense.
Okay, so this is going to say that exact same thing. Every input has a unique output. A relation R, first off, let's remind ourselves what is a relation. It's a 2-term predicate. It takes 2 terms and spits out true or false. Okay, a relation R is said to be functional, provided that for every x, for every input, there exists a unique y, a unique output, such that x is related to y.
So where do
Every x is related to one and only one thing.
are we kind of defining what a function is?
Sure. It's a notion of a function. When you get to, fast forward to your algebra class, we're going to have a definition of a relation. A definition of a relation now is a set theoretical relation. A relation is defined to be a set of ordered pairs. That's going to be the definition of a relation eventually, and from there on out in all your higher level fields of math, that's what people mean by relation.
Not a 2-term predicate?
Not a 2-term predicate. We can always encode a 2-term predicate in here. When I say that A is related to B, that's logically equivalent now to saying that the ordered pair AB is in R.
They're real numbers.
Sorry. Is in this relation.
Oh.
Okay.
Sorry.
I was
sorry.
close too.
Yeah, that was a terrible mistake. I did that way too much with my R's. So that would be your definition of a set theoretical relation. And it's now everything that's true about this relation
That makes sense.
is true for relations in logic.
That makes sense, I guess.
It was always confusing to me to have the, when they were like f of x is this and this and that. Like it was never.
You mean like what function actually was?
Mhm.
Yeah, they never explained that.
They never actually explained what a function was. So they're just like, here's your function.
Yeah, so relation is just a set of word pairs. Let me draw a relation. A1, B2, A3. There's just a random relation. A function is a relation where every left-hand element maps to a unique right-hand element. This relation is not a function because I have A paired with 1 and A paired with 3.
Right.
So R is a relation, R is not a function. If I replace this A here with a C, R is a relation, and now it's also a function.
Wait, so how is that definition of a set of ordered pairs encoded in that first definition up there?
It's not.
Oh.
I'm saying this is what you would ultimately get to.
Oh, okay.
And so we're talking about a functional relation,
Uh-huh.
and it's giving us more of that foundation, but we're not ready for a function is a relation with this property where we're not ready for our set theoretical relations and functions yet.
Okay.
And we're getting there. That's why I hesitate to say, is it a function? Sure.
Okay.
Everything that's true of functions is going to be true of these things.
Function of functional relation.
Of these functional relations that we're about to define.
Okay.
So a relation R is said to be functional, provided that for all x, there exists a unique y such that x is related to y. Notation that we use, special indication of functions, if it's a functional relation. When we say x is related to y, we can also write that as y is equal to r of x. Y is a thing paired to, y is a thing x is paired to using relation R.
Understandable. Okay.
When I plug x into R, I get y. When I plug x into R, I get y. Maybe it would have been better if I wrote it this way. R of x equals y.
Yeah.
variable y. So this is valid notation when you have a functional relation. It is not valid notation for just relations in general. Again, jumping ahead, just as an example, let's say R is equal to the relation A goes to 1, B goes to 2, A goes to 3. If I then say what is R of A, what's the thing paired with A? Is it 1 or is it 3?
Well, it's not a functional relation.
It's not a functional relation. And so I'm giving you intuition for why this notation isn't defined for relations in general. It's only defined for functional relations that we can use that notation. Because every input will have a unique output. And so the notation is well defined. So that's why that notation, and we can use that notation for functional relations, but not for relations in general. Anyways, so we have this. A relation R is said to be functional, provided that for all x there exists a unique y such that x is related to y. Notation, x is related to y means that R of x equals y. Okay, so there's a definition of a functional relation. Now, the image of a functional relation R on the set M, which we denote by IM R of M, is the collection of all y for which there is an x in M such that x is related to y.
What's a collection?
Yeah, what's a collection? You can take issue with that. We'll take issue with that here in a second, but first let's wrap our head around it outside the word collection.
Okay.
So, again, let's just pick some example. So M is just going to be some set. Pick a set for me.
Set
AB. And now, well, let's use numbers just because numbers are easy to work with. So we'll make this 1, 2, 3. And we'll pick R. R now we need to make it some functional relation. Using notation that we haven't defined yet, but just jumping ahead. I'm going to say R of x is equal to 2x. Or in other words, it pairs to double of what you give it. So 1, using this relation, is related to 2. 2 is related to 4. And 3 is related to 6. Using this relation on this set.
So the image of that.
And so what we're talking about here now, the image of R on M, what we mean by,
Oh, I see it.
so rewrite this down, R of x is equal to 2x. The image of R on M, 1, 2, 3, is a collection of all y's, all outputs, that M is related to under this. So we checked what 1 was related to, it was 2. We checked what 2 is related to, it was 4. We checked what 3 is related to, it was 6. And so the image of R on set M is a collection of 2, 4, and 6. It's the collection of 2, 4, and 6.
It's not the set 2, 4, and 6?
So far, it's the collection.
What is the collection?
Don't worry about it. Because now, axiom 5 is, let M be a set and R be a functional relation, then the image of R on M is a set.
Why can't that just be part of the definition?
Because I can't just define sets into existence. I might accidentally do what Bertrand Russell tried to do. How do I know that this thing is in fact a set? So I'm saying take all those outputs, but how do I know that all those outputs together constitute a set? And so axiom 5, all it does is tells us that the output of a functional relation is a set.
There's no way to arrange this to where that could be a theorem, and it's not part of your axiom. We can't somehow prove that the image of the relation is a set.
No, because we don't know what the image of these things even are, the things related to them. So we take all those things, how do I know that those things constitute a set? In other words, we need an axiom that tells us that when you apply functions to sets, your output is sets again. That's essentially what it's saying, and we need something that tells us that.
That's really annoying. Okay.
So, any questions as to what this axiom means? Ultimately, the main purpose of this axiom is it's the axiom that gives us set builder notation, surprisingly. And it's the one that gives us pretty much all the interesting stuff that comes up. Well, I should say that, but gives us a lot of it. So you feel like you understand what the axiom is saying?
Yeah, that kind of makes sense.
Yeah.
All right. So going to define some notation, just so we don't have to keep doing this over and over again. When I say for all x and y, such that p of x,
Is that a functional relation?
so this right here, how would we normally read this? We're saying for all x and y, p of x is true. That's how we would read this. You've already seen notation like this going back. You've seen me write something like, for all x, y in the real numbers, x plus y equals y plus x. Right? It's very useful to have this notation, where it's for all x and y from a set, rather than saying for all x and y across whatever, just anything, and have it being not stated exactly where they are. So I want to be able to talk about for all x and y in a set, rather than just always having to say for all sets.
Okay.
So we're going to define this notation. For all x and y, some predicate about x, we're going to define that to mean for all x, if x is in y, then p of x is true. That's what it means for all x in y, p of x. It means for all x, if x is in y, then p of x is true. P is true for x. That's just what we're going to define it to mean. So that we can start using this notation.
That makes sense. Okay.
Similarly, when we say that there exists an x and y such that p of x, we're going to define that to mean there exists an x such that x is in y and p is true for x. For any predicate p here.
Predicate.
Yeah, p is just a predicate.
Okay. It's not a functional relation.
No, so put a pin in this for a second. P here is just some single term predicate. Give it x, it spits out true or false.
How can you tell the difference between the functional relations and like predicates?
Just from notation alone, it's not obvious.
It's just convention.
And so you often have to infer from context.
Okay.
And so as a general rule, once we get down to functions, as a general rule, you use letters like F, G, and H to talk about functions. And when you're just talking about a relation in general, you use capital letters like R.
And predicates of
Okay.
P, I assume?
And predicates, yeah, predicate pretty standard to just use a capital P. So this is just a predicate like from logic, P of x, just letting us know it's a single term predicate. Takes one term.
Okay.
So for all x and y, P of x, we define that to mean for all x, if x is in y, then P of x is true. That's what we mean for all x and y, P of x.
Okay.
Similarly for the one that there exists. Now technically we don't need this as a definition. You could get this as a theorem from this.
I should have asked this earlier.
Go ahead.
What's the IN
It's the image.
Image. The
Oh.
image of R on N.
That's
what this was. The image of R on the set 1, 2, 3 was 2, 4, 6.
Okay, yeah.
And so the axiom here is saying that this collection of things that comes out is in fact a set.
Which makes sense.
So when I run a set through a function, the output is still a set. That's what it says.
Okay.
Good?
Yeah.
Okay, and then that's just defining notation. You could have already guessed what this notation meant, but make it explicit. Okay, theorem 3, the big one. Euler's theorem in set theory that we're going to be doing. Let P of x be a predicate, any predicate, and M is just going to be a set. Then the elements y in M that satisfies P constitutes a set, and we denote it with the set builder notation. The set of all y in M such that P of y is true. Let's draw out a concrete case. Where do I have examples that I can erase? This was just a bunch of examples. Okay. So let's write out a concrete case really quick. Let's say M is equal to the set 1, 2, 3, 4, 5, 6. And we'll say P, this predicate, P of x, is going to be equal to the x is even predicate. With me so far?
Okay.
So here's what we're proving. Let P of X be any predicate. Here's just an example. P of X is a X is even predicate. And M be a set, any set. In our example, we're just going to use a set 1, 2, 3, 4, 5, 6. We're trying to prove, then, that the elements Y in M, picking out all the elements from M, such that Y satisfies P, constitutes a set. So in other words, if I pick out 2, 4, and 6 here, if I choose those out of here, I basically run this filter on this set, the result is still a set.
Yeah.
And that set is what we are going to mean by this notation, this set builder notation. So we denote it, it's going to be the set, all Y in M, such that P of Y.
If there's no even numbers in M, then is it just an empty set?
Then it would have just been the empty set. So we are defining this notation. So when I say the set of all Y in M, such that P of Y is true, up here, then that is equal to this set, 2, 4, 6. That is the set of all Y in this set, such that Y satisfies the P predicate.
Right. Yeah, I was gonna say, predicates, I don't know, like putting that filter on it kind of feels like domains almost.
That's exactly how we're going to think about it, is this is a domain, and we're going to run it through a function, and this is going to be its output. And we're going to be using the fact that the output of a function on a set is a set. Our whole argument is trying to argue that this thing here is in fact a set. That's what we're going to be proving.
That makes sense. Would you say that a set is a domain, or is it like...
A domain is a set, and an image is a set.
A domain is a set. Okay, that makes sense.
Yeah, so up here, this M was basically functioning as a domain.
Yeah.
And the image of M on R was basically functioning as the image, or I guess you're used to the range. I might say image, I might say range, same thing. It's just when you get to more advanced math, everyone says image. Nobody uses the word range anymore.
Why did they use range in the...
I don't know the history of these terms and where they come from.
Why do they say image?
I don't know the history of these terms and where they come from. No idea. Okay, so that's what we're trying to prove. If I take M and some predicate, and I kind of run that predicate as a filter on M, the result is still a function. Or sorry, the result is still a set, and it's what this notation captures, this set builder notation. It captures that exact set. So let's jump into the proof now. So let P of X be any predicate, and let M be any set. Now, we have one of two cases. Either there is something in M that satisfies our predicate. So in this concrete case, either there's something in M that is even, or there's not. It has to be one of those two cases. Something in M that satisfies a predicate, or there isn't something in M that satisfies a predicate. So if it is not the case that there exists Z in M such that Z satisfies the predicate, then when I run the filter on M, what am I left with? If there's nothing in M that satisfies the predicate, then what am I left with when I run the filter on M?
The empty set.
The empty set. So if it is not the case that there exists Z in M such that Z satisfies P, then we define this set builder notation to signify the empty set. So then Y is in M, or the set of all Y in M such that P of Y is true, is just the empty set. So if there was nothing in M that satisfies the predicate, then this set builder notation, the set of all Y in M such that P of Y, simply signifies the empty set. Now, let's handle the case where there is something in M that satisfies our predicate. If there does exist Z in M, such that Z satisfies a predicate, we are now going to come up with a functional relation that we can run on M, whose image is 2, 4, 6, whose image is the things out of M we were trying to filter with our predicate. And if we can come up with a functional relation that we can run on M whose image are the things that satisfy that predicate, then the things that satisfy that predicate will in fact be a set. Remember, ultimately what we're trying to prove is basically running that filter on the set results in a set. So, the hard part of this proof is coming up with some functional relation I can define on M, whose image would spit out 2, 4, 6. Whose image would spit out just the elements of M that satisfy predicate P. And so here's exactly how I'm going to define that relation. So if there exists Z in M such that Z satisfies P, we're going to define the functional relation on M, and here it is. X is related to Y if and only if one of these two things are satisfied. We have this or this. Either X satisfies P and Y is equal to X, or it is not the case that X satisfies P and Y is equal to Z. In other words, we are taking each thing out of M, and we're saying, does this thing in M satisfy our predicate? For example, does 1 satisfy this predicate?
No.
Or sorry, does 1 satisfy this predicate? No. So if it does not satisfy the predicate, we're just going to map 1 to Z. What was Z? It was just something in here that satisfied it. So looking in this concrete case, let's say that M is this thing and P of X is this thing. We're not, in case 1, it's not the case that nothing in there satisfies a predicate. It's the case that something in there satisfies a predicate. Tell me something in here that satisfies a predicate. Doesn't matter which one. So 4. So Z in that case, we'll think about Z as being 4. Okay. So what is my relation here going to do? It's going to take each X out of M. It's going to take each one of these things, and it's going to pair it with something. It's going to map it to something. And here's how we figure out what to map it to. If P satisfies it, then we're going to map it to itself. If it doesn't satisfy P, we're going to map it to Z, whatever our Z was. So 1 is related to, using this relation, let's see, does 1 satisfy the is even predicate? No, so we're in this case. Does 1 not satisfy the is even predicate? Yes. So then Y has to be Z in order to make this thing true. So in other words, we're pairing 1 with 4. What is 2 related to?
2.
Well, let's see. 2 satisfies it, so the Y has to be the X. That's the only thing that satisfies it. So 2 is going to be related to 2. What is 3 going to be related to? Once again, 3 doesn't satisfy it, and so it's just only going to be related to Y when Y is equal to Z. And so 3 is going to be related to 4. And now, what is 4 going to be related to? 4. And what's 5 going to be related to?
4.
And what's 6 going to be related to?
6.
So if it satisfied the predicate, we just mapped it to itself. And if it didn't satisfy the predicate, we just mapped it to something that for sure did. And so now look at the image of this set. What is the image of the set? 4, 2, 4, 4, 4, 6. The image of the set is everything in M that is even. Our whole job was to come up with a function that we could run this through, whose image is all the things that we cared about out of this set. Why did we need to come up with a function whose image is all the things we care about out of the set? Because we're guaranteed then that the image is also a set. So that essentially gives us that I can take this, view it as a filter on this set, and the result is still a set, which is what our set builder notation is. Our set builder notation, the way I think about this, all Y in M such that P of Y is true, we think about that as a filter. We can think about this as a set of all Y in the integer such that Y is even. Could have been a way of thinking about that. So this gives us our set builder notation. So X is related to Y if and only if one of these two things happens. Now I rewrote this out. Sorry, this is nothing. I rewrote it out using our functional notation that we know and love. What is X paired to under R? Well, if X satisfies predicate P, it's just mapped to X. And if X doesn't satisfy predicate P, then it's mapped to Z. If X satisfies predicate P, what was our output? It was just X. If X didn't satisfy predicate P, what was our output? It was just Z, whatever Z was. Or in that concrete case, we're saying that R of X, using that concrete case, is equal to X is even. If X is even, we just spit out X. if x is not even, or odd, but not even, then we just spit out 4. And now everything that it spits out is even. Because it either spit out x, which was even, or it spit out 4, which was for sure one of the even things in there. So then, if x is related to y, and x satisfies p, in that case, then our output y had to be x. And so we get that y was in M, and y satisfied p. Similarly, if x is in R, and x did not satisfy the predicate, then our output y was equal to z. And so once again, we get y is equal to M, and y satisfies the predicate. Because remember, z by definition was something in M that satisfied the predicate.
You said it is equal to.
Oh, sorry.
Sorry, yeah.
So I'll say this again. X related to y. If x doesn't satisfy the predicate, then our output y had to be equal to z. And so y was something in M, because by definition, z was something in M. So y is something in M that satisfies the predicate.
Okay.
And so, in either case, we got it. We got all the y's and m's that satisfy the predicate. All the outputs here satisfy the predicate. And so then, the set of all y and m such that p of y is in fact the image of r on m. And I got the image of r on m is a set by axiom 5. Therefore, this set builder notation does in fact give me a set.
Okay.
A lot to swallow there. Hardest one to absorb.
Okay. That makes sense though.
Any questions on that?
No, that makes sense.
It's one that I had to stare at for like 5 minutes before it finally clicked in my brain.
Yeah, I guess that makes sense. Kind of weird that you define something in your proof.
Well,
Yeah.
my whole goal here, remember high level what I was trying to do. I was trying to say, start out with a set. Pick some predicate that you want to use to filter the set.
The result is still set.
I won't argue that the result is a set. So the whole goal was to come up with some function that does that. Because I know that the image of a function is for sure a set.
Oh, so you just define a function.
So the whole name of the game was to try and find some function out there that does it.
Oh, that makes sense.
It's kind of like when you're trying to prove, I don't know if it's kind of like it, but I'll say it. It's like going back to topology, how do I know that this set is homeomorphic to this set? Or this topology is homeomorphic to this topology? Can I find some homeomorphism that does it? If I can, then it is. So the name of the game was, can I find the function that does it? And if I can, then yes, it's a set. Okay, anything else feel weird or that we don't like?
No, that makes sense.
Good? Okay, now let's define some more operations. Remember, our only operation so far is union. Now we're going to use union to define all of our other operations.
And union was an undefined term, right?
Union is an undefined term. It's one of our primitives. So union shows up in axiom 4.
Okay.
Okay, so now, definition of intersection. The intersection on X, what is that going to be? It's going to be the set of everything in the union on X, such that for all B in X, A shows up in A shows up in that B. So again, these new ways of defining union and intersection, it can be a bit hard to absorb the first time, but with concrete cases, I think it makes it pretty clear.
Intersection. Okay.
So let's draw it out with this concrete case.
Okay.
So here's my set A, here's my set B, here's X, which is equal to A and B.
Yep.
So what is the intersection on X equal to? That's the same thing as the intersection on, just writing it out explicitly,
AB.
just super explicitly. So writing all the elements, I think that'll be the best way to say it. Now, intuitively, what is the intersection of these two sets?
Let's see.
It's intuitively, you know that we expect this to come out the set just containing C. Here's a set of everything that shows up in this set and this set.
Yep.
Right? Now let's see how we get from this. So this is equal to, let's see, this is equal to the set of all A in the union of X. So in other words, we've got to check A, B, C, D, and E. All A in the union of X, where for all B in X here is going to be one of these sets.
Okay.
A shows up in that set. So my first A here is going to be little a. Let's see, does A show up in this set?
Yeah.
Does it show up in this set?
No.
So it's not in my intersection. Because for all B, A has to show up in there. For all B in X, A has to show up in B.
I see.
What are the elements of X?
It's A, B.
Big A and big B.
Mhm.
Okay.
So it has to be the case that for everything in X, which would be this and this, little a shows up in that thing. So this has to show up in big A, and this has to show up in big B if it's going to show up here. But it doesn't. What about little b? Does it show up in big A?
Yeah.
Yeah. Does it show up in big B?
No.
No. So it doesn't show up here. What about C? Does it show up in big A?
Yeah.
Does it show up in big B?
Yes.
So it shows up here. What's the intersection? It's the set of all A in X, in the union on X, such that for all B in X, A is in B.
Wow. Why do we need the union of X there? Why can't we just say A and X?
Okay. So you want to say, this is stupid. We should just say it means it's a set of all A such that for all B in X, A is in B, right? And now we are back to what we call naive set theory. In fact, this is the backbone of Russell's problem. And the problem that we had in early set theory is there was this assumption that if you could in some meaningful way, talk about the set of all things satisfying some condition, then that should constitute a set. We call it naive set theory, and we kind of pretend that's true in most simple set theory cases. But then notice that I can define U this way. U is going to be a set of all X such that X is not an X.
Wouldn't usually be the end set.
No. Here, U is a set of all X such that X doesn't contain itself.
Oh, that's your problem right there.
That's exactly what this U was right here, that we started out talking about. We know that this is in fact not a set. And so if we allow naive set theory, if we allow you to just use set builder notation like this, then you can define sets into existence that aren't really sets. And so the set builder notation that we have is more restricted. We have to specify all the elements are coming already from a set.
Okay,
So we always have to say the set of all A in something. We can never use the set of all X. It has to be the set of all X in something. We have to make sure already that we're only selecting from a pre-existing set.
okay.
And it, in a sense, stops us from labeling things that are too big as sets.
Okay. So why don't, in this case, why don't
How
we
would they
say...
be too big? What do you mean by that?
When we get collections there are collections that are too large that they're not sets anymore. So there's a notion of what's called a proper class. And it is too big to be a set.
Okay, but like domains are sets, right?
Domains are sets, ranges are sets on set theoretical functions. Yes.
So it's bigger than a domain.
It's bigger than...
It's we're kind of not ready to talk about these things yet. We wouldn't really talk much about them anyways. But the point is, look, the set of all sets that don't contain themselves, that collection, it's too big to be a set. It's trying to capture too many things,
I see.
in some sense.
Okay, so going back to this definition, why can't we say A in X? Why does it have to be A in the union of X?
Because X here is this. Collection of sets.
Right.
That's not what we mean by the union. We're not talking about checking big A and big B. We wanted little a, little b, little c. Little c, little d, little a. And so the elements that we're interested in sticking in the intersection are not big A and big B. It's little a, little b, little c, little c, little d, little e, which are the exact elements of the union on X. So what are the elements of big X? That's big A and big B. What are the elements of the union on big X? That's little a, little b, little c, little d, little e, which is what we want to show up in the intersection of these things. We already had our notion of what we wanted that to be. We wanted that to be the set containing just C.
I know you told us, but I want to make sure I know the notation. So, union is the U, and then intersection is the. Okay.
And so it can be kind of tedious. We'll see that down the road, how not using naive set theory gets tedious. I'm jumping the gun. Anyways, so here's that definition of intersection, and you see how it gives us exactly what you would expect from the intersection. Now, once again, we could define the notation you know and love. I could say the intersection A intersect B. I can now define this to mean take the intersection on the set containing A and B. And now we can use that notation.
What you do over there, right?
I'm sure I have it up here. Yeah.
Yeah.
Oh, yeah, literally right there. Okay.
Okay.
So we now have intersection defined. And now we can define the complement of a set, or set difference. What is X minus Y? We want that to be the set of all A and X where A is not in Y. And so, coming back down to this, let's say X is big A minus Y is big B. What's A minus B? It's a set of everything in A that's not in B.
So
Let's see, little a is in A. Is little a in B?
Oh.
Nope, so it's in the set difference. Little b is in here. Is little b in here? Nope, so it's in the set difference. C is in here. Is C in there? Nope. Or yep, so it's not in the set difference.
So it's everything that's not in the union, or
It's everything in A that's not in B.
in the intersection.
Okay, so if it was B minus A, it
It's-
would be D and E.
The set of all A and X where A is not in Y.
So it's like the
That's what X
everything-
minus Y is.
Everything in A that's not in the intersection of A and B. Is
Yeah.
that a valid way of thinking about it?
Yes. If we were to write a quick Venn diagram where this is A and this is B, A minus B is A. Now subtract everything from B. Well, these are the only things that we can subtract that were in bold. So when you subtract away this piece, you're left with what's over here. Probably should have colored in what we were left with, but yes, that's one way you can think about it.
That makes sense.
And then if it was B minus A, it would be D and E.
Perfect. Notice that subtraction here is not commutative. And so B minus A is a very different set. B minus A is everything in B that's not in A. And so in that case, it would have been DE.
Is there a set addition, or is it just set subtraction?
There is set addition in the sense that you can union sets together.
Okay.
We don't have a plus symbol defined on sets.
Weird.
And this subtraction symbol is sometimes not used. Sometimes they do it A slant B like that. It's another common way it comes up. Okay, so define those new operations. So now we know a few operations on our sets. We have a few relations, and the only term we defined our set was a empty set. Okay, so now axiom 6. Sorry, you erased so much of this. Let M be a set. Then there exists a set, denoted fancy P of M, whose elements are precisely the subsets of M. We call this the power set of M.
Yeah, that's right. I remember that topology.
So for all M, there exists a U, such that A is in U if and only if A is a subset of M.
Okay. Wait,
U is equal to the power set of M is the notation we use to denote it.
why is that an axiom
That the power set exists,
yeah.
because otherwise there's no way for you to get the power set.
How? Because it feels like with what we have, we should be able to prove that.
So let's really quick think about this, what this gives us. So concrete case. Let's do an example. What is the power set of the set containing AB? It's the set of all possible subsets. So one subset of this is the empty set.
Yep.
Everything that's in there is in there. Another possible subset is the set containing A.
set containing B.
Another possible subset is the set containing B.
And the set containing AB.
And then another possible subset is the set containing A, B.
Is that not, can we not get that from what we have already?
Can we not get that from what we have already?
All of our definitions and axioms and theorems, can we not use those?
My gut wants to say that we can for a finite case. So I think if we're finite, we can. Let me think about that. So, we know that A and B would be sets, that would be given to us. And so the set containing A and B is for sure a set.
Well, we know the set containing A and B is a set.
And so, my gut is yes, that for any finite set, we can construct its power set without the axiom.
Mm-hmm.
But now, once we get an infinite set, there would be no way for us to construct its power set using this stuff. And so it would have to be given to us that its power set is still a set.
Have we talked about infinite sets yet?
No. Axiom 7 introduces us to the infinite set. It's the set that gives us the natural numbers, essentially. Is Axiom 7.
Gotcha. So, and just a quick note, the power set is the same thing as the discrete topology? Question mark? What evacuative topology? You had your trivial topology and your discrete topology. Your discrete topology was the power set.
Yes.
Okay.
The discrete topology was the power set.
Okay, that makes sense.
Okay. So here's the power set of the set A, B. So let M be a set, then there is a set denoted, the power set of M, whose elements are precisely the subsets of M. So for every set M, there exists a U such that A is in U if and only if A is a subset of M. So U would be the power set of M. So if this right here were M, then what we have written over here is U. This is U. Everything in U is all the possible subsets of M we could write.
Yep.
Put together in a collection.
Okay.
So now we kind of already had this conversation. It would be very natural for us to have thought to use set builder notation like this to define the power set. What's the power set on M? It's a set of all X, such that X is a subset of M. Again, why couldn't we just define it into existence like that? Because we would have needed some X to take that set from.
Right.
And so we need to ensure, basically, if we just use that notation, it could have been the same problem where we could have accidentally been defining things into existence that weren't actually sets.
Yeah.
Okay. Now, naive set theory, we don't bother specifying what set we're selecting from. Strictly speaking, we have to. Strictly speaking, anytime we use a set builder notation, we have to say the set of all y in some set such that some condition. Now, even though set builder notation can get us in trouble, or naive set builder notation can get us in trouble, it is a notation that everybody uses.
Yeah.
And we only actually use this careful thinking when we just need to be extra careful, but nobody really uses it. Why does nobody really use it in practice? Well, I'll give you an example. Let's look at this bottom one, defining a new operation on sets. X cross Y. This is a set of all ordered pairs A and B, where A comes from X and B comes from Y. You with me?
Yeah.
Let's just write out a concrete case down here really quick, just to get comfortable with it. So let's say that X is a set 1, 2, Y is a set A, B, C. What is X cross Y? It's a set of all ordered pairs we can possibly make, where the first element comes from this set and the second element comes from this set. So we could have 1 goes to A, we could have 1 goes to B, we could have 1C, 2A, 2B, 2C. These are all the possible ordered pairs we can make, where our first element comes from this set,
Okay.
and our second element comes from this set.
I was wondering if you could reverse it like it.
Right, this is very different. This is not the same thing as
Y cross X.
Y cross X. Sorry. Y cross X.
That makes sense. Okay.
Because y cross x would be a goes to 1, a goes to 2, b 1 goes to 1, b goes to 2, c goes to 1, c goes to 2. Okay, so very different. Okay, now if we were to be completely proper, what exactly is x cross y? It's a set of all a, b, and c in the power set of the union of the power set of the union of x and y, unioned that thing with x. Here is the set we would have to select ordered pairs from.
Oh. Like, I guess oh, okay. Oh, that makes sense. Alright.
And to give you a sense of how fast this blows up, already unioning x and y together here, if that were this, so if x and y were this, the unioning of x and y, that now has 5 elements, right?
Yeah.
The power set on a 5 element set has 32 elements.
Yeah.
Union that with x gives us
37. Or, sorry, 34.
34 elements. The power set on 34 elements is roughly 16 billion elements.
That's a lot of elements.
Sounds like a lot.
That is a lot. And so writing that out explicitly would be a humongous nightmare. Remember what 4 looks like.
That's an understatement, yeah.
Yeah. So, that's why so naive set theory, even though it can get us into trouble, it's what everybody uses. Why?
It's easy.
Because that's a nightmare. Right, it's
Wait,
easy.
why do we have that last power set right there? Why can't it just be the union of the power set of the union of x, y?
You would have to just play around with it, following just one element, and see how it gets generated.
It's very interesting. Yeah, it's not very obvious from
Yeah.
looking out.
The way I recommend, if you want to play with that, is you do it with an AI, having it generate the element for you.
That's fair.
Because that's what I did to confirm to myself, oh, yep, that is what the domain would need to be.
How did anybody find that out?
There's a way to just think through it and see it come out. But we won't bother with it. So the point is, we don't bother, even though it's the correct way to do it. It's the proper way to do it, nobody does it. So all these things that we've been defining have their naive set theory definition counterparts. And so I want to expose you to those because those are the ones that you are most likely going to see if you just take some random math class. So we define x union y as the union on x and y. Now, chances are if you take some basic high school class, when you see x union y, here's the definition you're going to see. It's a set of all a's, such that a's in x or a's in y.
That's what you gave. That's what you give in your set theory.
Right. This is exactly what I would give in geometry as a definition. In geometry, we're only going to use naive set theory. I'm not going to introduce all the axioms of set theory to you.
Right.
And so that's the definition you're actually given. And for intersection as well, x intersect y, rather than defining it as the intersection on x and y, instead we define x intersect y to be the set of all a's, such that a's in x and a's in y. And so that's the naive set theory definition. And it's very useful definitions because then you can quickly see the relationship between union and or and intersection and.
There's no way to we can't say find a set that A is in that would satisfy that. If you know what I mean.
I'm not certain. You mean.
So we can't say x union y is defined as A in a set B such that A is in x or A is in y, where B is a certain set.
We could have come up with this as a theorem for this is the same thing as that. We would just have to specify the A's that we come from.
Is there any way to have, so my question is there any way to set up the naive set theory definition properly without having to have union as part of your axiom?
Without our union axiom that we had from the beginning?
Yeah.
Now, our union axiom is one that gives us all of our operations. They're always using union. Our definition of our operation here,
Right.
well, I guess this technically wasn't using the union.
Well, it's just, that naive set theory definition feels like it's a good definition.
Well, yeah, it's a very natural definition. It's a very intuitive definition. There's a reason that we love it, and there's a reason that we use it. It's because it's so easy to work with, it's so nice to work with, and it makes you see the connection with logic very quickly.
I guess my question is, why can't we create that definition?
You can. It's just now not a definition, it's a theorem. We can prove that this holds. It's just we have to change our notation here. Because strictly speaking, this notation is nonsense.
Right.
I need to say, and in this case it would be kind of stupid. It would be the set of all A in union,
Oh.
right? X, Y, such that A's in X or A's in Y.
Oh, I see. Okay, that makes sense.
And so you could define it, you just have to specify the domain we're selecting from each time.
Which is what I was asking about.
Oh yes, you could always just give it a domain on, slap a domain on there, and then yes, it would work. And it's just a matter of finding the domain. So like when we defined the cross product here, it's almost an identical definition. The only hard part is finding that domain that we're selecting elements from. That's what becomes tedious, that's what becomes a pain. But once we can find that domain that we're selecting elements from, then it's identical. It's just changing that we gotta specify the domain that it comes from.
Gotcha.
I shouldn't say domain, the set that it comes from.
Yeah.
In other words, we're always making sure that we're only selecting from sets. So we don't accidentally define things into existence as sets that aren't really sets.
Right.
So it stops us from doing stuff like this, a set of all sets that don't contain themselves. So technically speaking, you should always and forever be able to say what set we're selecting from.
Right.
Okay. Before we get to the naturals, quit right before the fun stuff. Shoot. All right, we'll call it there.
Okay.
We're finishing next week, right?
Yeah, we'll finish up next week, and we will be voting. We'll take time to vote on what to do as our next course, and so the first like 20 minutes of class will be that.
Okay.
Okay.
Parley will be here too. We'll probably not finish that theory.
Well, hopefully they watch it and want to stick around towards the end. Because yeah, we're so close to all the fun stuff.
How much more set theory is there?
That's just right here.
Oh, that's
I was hoping we would finish.
Well, we can take an extra 20 minutes.
I don't know, because this is getting a spur conversation.
Okay.
Alright.
That's valid, I suppose. Okay.
So I'll figure out some stuff to add on next week that will be fun for us. Anything else we haven't recorded? Okay, see you guys next week.
What are the 4